Welcome everyone. This is the second session of the workshop for game theory in blockchain. Our first speaker will be Shijef Wasserkrok and Eitan Fachi. So Shijef will give the talk, right? So let's turn to Shijef, please.
Okay, just to make sure, can you hear me? Hello?
Yeah, please. Yeah.
Okay. Thank you very much. It's a great pleasure to be here. And I'll present a game-theoretic model for strategic competition in business networks. This is joint work with my colleague, Eitan Farhi, and we're both from IBM Research, working out of Israel's Haifa Research Lab. So what we're seeing is that permissioned blockchain is becoming the infrastructure for many business networks, both existing networks and new ones. What we mean by business networks are several enterprises coming together to jointly provide some value. So perhaps an example that I'll use throughout this talk is a transportation network where we have shipping companies, terminals, inland transportation carriers like trains and so on, all coming together to deliver cargo to end customers. But there are also other types of business networks, like supply chain. For example, we have retailers with suppliers and the farmers and so on. There can be financial networks, banks, stock exchanges, and so on, trading goods, which are not tangible goods, but paper goods. And of course, we're all familiar now with medical or pharmaceutical networks that are being used to transport drugs, medicines, and now hopefully vaccines throughout the world. And what we're seeing is that, as I mentioned, is that blockchain is both driving the creation of new networks, but also enabling through data sharing, through analytics, enabling the creation of new value for such existing networks. Now, what prompted this work is an observation that what we call strategic competition, which I will explain this term, is that typically business networks form when enterprises believe that their participation in such a network will be more valuable than not participating. That is, that they believe that their participation in a network will bring them value. But what this results is a very interesting setting that simultaneously combines both cooperative and competitive aspects, because they want to cooperate in order to increase the network value. If the more value they can provide, intuitively, the more value each participant can gain. So this results in cooperation. But on the other hand, there's also competition, because once the value of a network is set, then there's sort of a fixed value, a fixed sum that needs to be divided between all of the participants. And this is what we call strategic competition. And this is very intuitive. So what I'm going to present in this talk is how we formalize this notion and some basic results regarding the behavior of such networks. So to kick off, I'll start with a very simple example, which I'll use throughout this talk. So think of a very simple shipping network where we have two shipping companies, S1 and S2, and two cargo owners, C1 and C2. And the cargo owners, if they can get a good delivered to them, they can sell it. Cargo owner 1, C1, can sell the good for P1 value, and cargo owner 2 can sell the good for P2 value. So just to introduce some notation that we're using here, we're showing basically two flows. We're representing business networks as a graph, and we're showing two flows. One, the flow of goods. So, and we see, for example, C1 flowing the good outside and getting a value in return, similarly for C2. But in order to have these goods, they need to have it delivered. And so they need some partners who can deliver these goods. So we have these two shipping companies, S1 and S2. S1 can transport the good, and we indicate this as an arrow going into S1, but the cost incurred is D1, and S2 can similarly transport a good, and the cost incurred is D2. So intuitively, these are the four participants in the network, and what we need to define, quantities which I mentioned before, is what is the network value, or it can also be termed the system surplus, and what's the utility for each player, or how is the value divided between the player. So we put, because we say these are the participants in the network, let us put a little border around the network and say that what happens is that C1 reaches an agreement with S1 that S1 will do the transportation of the good. For this, S1 will have to pay the D1, and once the good is delivered to C1, C1 can sell it for P1 value. And similarly, C2 contracts with S2 for delivering the good. S2 pays D2, and C2 can sell the product for P2. So we can see that in this case, and if we look at the value intuitively again, and I'll define this formula a little later on, we see that the total network value, that's the sum of the value coming into the network minus the value going outside the network, is P1 plus P2 minus D1 plus D2. And now all that remains to be settled basically is how the value is divided between the partners, and say that they decide on a very fair value division. They simply divide the profit between themselves. And so this is P1 minus D1 divided by 2. Each one gets a part. And so we have the flow of value between C1 to S1. And similarly, we have a similar flow of value between C2 and S2. But what's important for me to emphasize is that this is not the only way that value or could flow, the goods and value could flow in the network, because, for example, say, and here just for making the presentation, the slide a little less cluttered, we unified the arrows. So we're using a single double-sided arrow to denote both the flow of goods, which is the first quantity here, and the flow of value, the second quantity here. And it should be clear which goes in which direction. So say D1 is smaller than D2, then it makes more sense for S1 to transport both goods from a network value perspective. So both the goods, now C2 and C1, both contract S1 to transport the good. And now the network value is P1 plus P2 minus 2D1, which is greater than what was before because D1 is more than D2. And again, say they each respectively divides the value between themselves, and this results in S1 getting a much larger value and S2 getting no value. And of course, this is not the only way to divide the value between the participants. So now so I've mentioned a lot of many terms here in these examples, and I'd like to call them out a little. So what we see here, we saw this, the outcome of these games denoted as graphs with nodes between them. We see flows, two types of flows, the flow of goods and the flow of value. And there is some connection between them, obviously. And so what I'm going to present next is how we formalize all these terms into a single model. So the way we formalize it, we form what we call a strategic competition games. And so we define this as follows. This is a game over a set of companies, or any game over a set of companies C, where the outcomes is a graph composed of flows and flows of value, such that first we have a flow of goods conservation. So what I didn't mention, this is a very simple example, but our model in general also talks about cases where one good can be transformed into another good at a cost, or several input goods can be transformed into different types of output goods, again at a cost. So we want to have a flow of good conservation. That is, at each node, there is some transformation function that defines how input goods are transformed to output goods. and there needs to be this conservation where the flow of output goods is equal to the result of the transformation function and the results of the input goods flowing in. So this is one relation, this transformation, and the other is how do we define the relation between the goods and the value. So we define two cost functions or two value functions. One, EBI, which is what we call an external benefit function, which is the value provided to a node in the network, to a specific enterprise, by sending goods, a good vector G outside the network. And we also define a cost, which is the cost of transforming an input set of goods to an output set of goods that has to be paid externally. So again, think of manufacturing cost, think of the transportation cost that I showed in the previous example as an external cost, and the payment being paid to each of the cargo owners as an external benefit or as a value flowing into the network. And now, based on these, now given a specific flow, so we say we have a game, the outcome of a game is such a flow that meets these conditions. And now, given this game, we define the two quantities that I mentioned. One is what's the utility of the player. And so the utility of the player is basically the flow of values of the incoming edges minus the flow of outgoing values. And I haven't defined anything. Note that what's being defined previously is these two functions, these external benefit and external cost functions that define how value flows into the network and outside the network. There's no restriction on how value is divided between the parties in the network. But so we define the utility of the players as the sum of the inflow value minus the sum of the outflow value. And we define the notion of the network value as the sum of the value flowing into the network from outside minus the sum of the values flowing outside the network. So this is a quasi-linear utility model, basically. And what we found to hold are two very core results, and they're not they're pretty straightforward, but they do show some interesting property. One is that the sum of the flow of each participant in the network is always equal to the total network value, and the second, and this is pretty straightforward. I'll go. The proof sketch is that if you just look at the graph and you look at the outcome of this graph, and you look at the sums on the left-hand side, right, which is the sum of the values, and you look at the sum on the right-hand side, you see this these cancel out because each internal flow basically cancels out, leaving just the outward flow. And this shows the first basic incentive for cooperation, which is that because what this means is that basically the increase in overall total network, what we call total network value, obviously results in more value that can be divided between the participants. So this formalizes the fact that there's an incentive to cooperate here. But this also shows the incentive for competition, because once you fix the T and V, then it's a fixed sum game. This captures the notion. There's a fixed sum game between the different participants in the network. The property two, and this is more interesting because the first one was more intuitive and it's very basic, is okay. So what we've shown in the previous property is that in principle, the value can be divided between the participants. Any additional value can be divided between the participants. But the question is, but what we've defined is that in this game, all the values must flow on edges in the network. There's no, it's not that goods can somehow be magically transported from an input to any of the players. They must flow on these edges between players in the network. So what so this second property says that actually any increase can potentially result. It doesn't need to now, and can potentially result in additional value to the players. So formally, this is defined and follows. So say we have a valid goods and value flow with a specific value, TNV1, and a good flow can be found that increases the TNV to TNV2, which is strictly greater than TNV1, then we can find a value flow so that the value for each participant is strictly greater than the value on the previous total network value. So this shows another, an even stronger potential incentive for cooperation. This is potential because if you remember my first example, when I showed the two values flows, the second value flow actually showed a case where the total network value increased, but one of the participants actually got a much smaller value. They got a zero value because they didn't need to ship any good. But and I'll explain that a little later on. But before I do that, I want to give the sketch for how this proof, for the proof of this property. So this is basically carried out by induction. So for the base, we have one enterprise. And so for the single enterprise, this holds by definition. As always, for a single enterprise, all the values must flow inside and outside the network. So this holds by definition. And for the step, what we do, we can arbitrarily select two nodes and collapse them into a single node. Just need to make sure that the value and goods flow is being maintained and is defined appropriately, how to collapse the value and the goods flow. And this with the same value, value as TNV1. And by the inductive assumption in this new network now, and a flow can be found with a greater value. So, and then can split it back into two nodes, again, dividing the surplus by creating or an additional appropriate edge between the two nodes that we couple together. And this shows the proof. What's very important to mention, though, is that this decouples the value flow from the goods flow, and I'll show this in using the same shipping network that I began with. So now let's use, this is the first shipping network that I began with, but now using concrete numbers just to illustrate. So say again, we have a similar scenario for, as in the first example, where shipper 1 and customer 1 agreed to transfer the good between them, and shipper 2 and customer 2 agreed to transfer the good between them. And we have now value. We see the value flowing into the network. C1 and C2 can each sell for 10, for a value of 10. For S1, the transportation cost is 2, the second number here. And for S2, the transportation cost is 3. And here, the total TNV is 15. And we can see how this is divided, that C1 gets 7.5, S1 gets half, C2 gets 6.5, and S2 gets 0.5. But we also showed a second flow where we get a greater TNV. This is the second goods flow, where S1 is doing the transportation of both goods. So this is the agreement. In this case, we have the TNV, which is 16, which is strictly greater. Here, S2 is not doing any shipping, but what we haven't decided is how to split the value. And so what can be seen is that the only additional value coming here, in additional unit, the only additional value is resulting from C2 having to pay less for the shipping, and so C2 is the only node that actually can see more value in this node. But now, say that we decide we want each of the participants to get more value, as we showed. So say we divide the new unit equally between the 4 participants, which means that C2 must actually transfer not only value to S1, but in order to get this value, C2 must transfer value for S2 for basically doing nothing, right? And let's put aside C1 for a minute. But the question arises, so this seems counterintuitive. Why should C2 pay S2 for not providing any good? So it seems that there's no good reason, but actually there is quite an interesting reason in this case, which can be formalized by the notion of stability. I'm not going to do formalization here, but just again to give some intuition. The idea is that C2, if S2 remains, this is to maintain competition, because as long as S2 remains a part of the network, as S2 is in the game, basically, C1 and C2 can drive down S1's delivery price to D2. That is to the price that S2 is willing to pay for shipping the good, because or has to pay for shipping the goods, because for any higher price being paid to S1, S2, it's always worthwhile for S2 to make a competitive bid and undercut S1 and deliver for less. So the only stable set, as long as S2 is in the game, the only stable set of contracts basically are those in which S1 is getting paid less than D2 for delivering the cargo. However, if S1 leaves, if S2 leaves, S1 can charge any price up to almost up to a profit, and it's still worthwhile. So any such price is a stable setting in the network. So again, this is just a very initial and basic intuition, but this can be formalized. So where do we go? So this is what the results that I wanted to present today, and where do we go from here? So what we define today is a model capturing the interplay between cooperation and competition arising in business networks. We described some initial formal results, formalizing the notion that an increase in network value enables increased network value to all participants, and showed through an example that why it's important to maintain the attractiveness of the network to all partners. So basically what we're looking for is not only how we can increase the overall value, but how can we increase the overall value in a sense that that is valuable for each individual participant. We don't want participants to leave the network. And where do we go from here? How do we build on that moving forward? So first, want to, as I said, the first step, and this is, we already made some advancements in this area, is building upon the work of Ostrovsky's work of stability in trade networks to create a distributed practical algorithm for finding initial feasible stable flow. What we mean practical is that not a limited amount of information needs to be shared about the contract. It's definitely in such settings, it definitely, the costs are not being shared. The parties don't know what the costs of the other parties are. And we want to find the relation between the optimal TNV and stability. We want to try and formalize in some sense what I showed earlier, that leaving the parties in the network, that is making sure that we have a stable set of contracts, requires making this profitable to all parties in the network. We, of course, are going to, additionally, is obtaining additional insights, doing analysis of specific games, looking at core concepts such as the core, shapely values, and equilibria, starting from simpler examples, seeing how, so this I talked about how finding initial flow, but we also want to find how to do, okay, so say, because usually there are already a set of contracts in such business networks, how can we take and help the parties form a set of contracts or form a set of agreements that increases the TNV while providing value to all the participants? And tying back to the role of blockchain, a very important role that blockchain can play in such settings, in addition to the one that it already plays, is being a distributed coordinator. For example, we're exploring if blockchain can serve as the coordination mechanism for driving or enabling correlated equilibria in such networks, because the correlation is very important by a trusted third party. We're seeing this as we're diving into examples. And so blockchain could potentially play a very interesting role here in being sort of this trusted, distributed third-party coordination mechanism. So that concludes my talk, and thank you very much.
Yeah, thank you. And any questions from the audience? Yeah, I don't get any direct questions. And maybe I just ask a few questions to clarify the model. So for the good, it's like it's coming in and going out. To be need to satisfy a condition. How many of them coming in, and how many going out at each node, right?
Yes, but it can also be transformed. So it doesn't necessarily have to be the same good coming in and out. There's a transformation function, for example, what I didn't show it in the network, but think of bread, right? So you may have flour and eggs and water coming in and bread coming out. So that's a transformation function. It says, how many eggs, how much flour, and how much water I need to make one loaf of bread. That's sort of the flow of goods.
Yeah, but value may stay in this.
What may stay? Yeah, value stays exactly.
Yeah.
And actually, that's a very good point. There is of course, more advanced models. If you're thinking of models like, or more advanced cases, if you think of models like supply chain inventory management, where also you may have goods staying between different time steps. We decided to start with a simpler model to analyze, but we think it can be easily extended to include such cases where also goods may stay, but then you have to define, but this also goes more to a repeated setting, right? Because then you have to define what happens between one step and the next. Yeah. This is easier to analyze in a single shot game.
Yeah. So how do we translate this into like in the in as an application for the blockchain network? How do we do that in that?
So there are two. So there are two ways this could be translated. One is to one of the value proposition of the. So there are many blockchain networks that are used by enterprises. For example, there's the TradeLens shipping network that ties together carriers and shippers and cargo owners and so on and ports. And there's also many supply chain in the retail industry. And one of the things that the blockchain is used to share data and to drive the joint processes between them. But what's often being done is that the data is being used to create increased value. Now, what you want to make sure is that this increased value being created by the data results in additional value to all partners, because otherwise what may happen, let me give you a very concrete example. So think of a supply chain network and say that as a result of getting data from the suppliers, the retailers, the supermarket can do a better job of inventory management and wastes less food, and so has to throw out less food. Right? And it's good for everybody. And this is the result of everyone sharing data on the blockchain network. But what could happen is that the retailer, as a result, may order less food from the supplier because they throw out less food, which would incentivize now the supplier not to report honestly on the blockchain network. So either the supplier stops sending the data on the blockchain network or sends incorrect data. So what we want to make sure that these do not happen. Right, so to make sure that the value is being maintained, this is the first tie into the blockchain network. The other tie is that if we could, through the blockchain network, enable the creation of additional value. For example, blockchain network, there are many cases. So we all know that mixed equilibria is not tractable, right? It's finding a mixed equilibria is not tractable, but correlated equilibria is polynomial. But there's often a problem finding, what's the coordination mechanism for creating the correlated equilibria. So blockchain, for example, could serve as such a coordination mechanism in these networks, enabling the creation of correlated equilibria between the parties.
Yeah. Thank you very much.
Thank you.
Maybe we can ask more questions later when we have a joint session to ask questions.
Absolutely.
Thank you very much.
Thank you.
Yeah.